Hello? Okay. So let's get started. Hi, my name is Erik Arvidsson, and I work on the Google Chrome team. And today I'm here to present ES6 and Traceur. And I'll also talk a little bit about AdScript and Angular 2.0, but the meat of the presentation is going to be ES6 and Traceur. So why does ES6 actually matter? Well, ES6 brings a lot of new improvements to JavaScript. And language improvements to JavaScript leads to a bunch of benefits, like better code and easier to maintain code, which in turn leads to happier developers. Today I would like to cover three main areas on how you can improve your code. So the first one is through ES6 features. ES6 is coming rapidly to all browsers. Browsers are starting to ship. Secondly, by making your own language extensions. With language extensions, I mean like introducing a DSL or doing code refactoring using Traceur or similar tools. And then make it part of your own build chain. And finally, a little bit about AdScript and Angular 2.0. So if you buy into the Angular 2.0 toolchain, you will get all the AdScript features for free, but also you get all the ES6 features for free. So what's new in ECMAScript 6? And how will it make you happier? I'm going to walk through some very common patterns from ES5 and show how it's done today and point out the issues with them and see how we can get around those issues in ES6. So first up is classes. So JavaScript is not a class-based language, but it's very common to use class-like abstractions. So JavaScript is a prototype-based language. And to set up a class-like abstraction, you have to go through a lot of steps. So in this example here, we create a point 3D which extends a point. So the first thing we have to do is define a constructor function. We call this point 3D, and it takes three parameters, x, y, and z. And secondly, we have to set up the prototype. And the prototype has to be a new object that has the prototype of the superclass in its prototype chain. And that's what object create does. And after that, we set the constructor as a property on the prototype, point back to the actual constructor. That's not completely necessary, but all the built-ins in JavaScript and in DOM do this. So there might actually be some code out there that depends on this equality. And finally, we add a simple method called equals. And if you look closer at the point 3D function at the top, you see the super call there using point.call this, which is going to call the superclass point constructor and pass in the current this. And similarly, at the bottom inside the equals function, equals method, we do the same thing. We delegate the x and y properties to the point class, and then we finally only handle the z property. And as you can see, this is a lot of boilerplate code just for this very, very simple class. I did the counting before, and there are actually 5 instances of point 3D in this text. There's 5 instances of prototype and 3 of point. So with ES6, we give you this very short and concise syntax. Class point 3D extends point. Exactly what you expect. We used to a mantra which we call say what you mean. The code should actually express your intent. In the previous one, it was impossible to see what your intent was without looking at the entire code base. So we define the constructor here, and we define a simple method. Same as before. As you can see, there's no mention of function anywhere. There's no mention of prototype anywhere. And instead of those ugly point.prototype.equals.call and passing this, we give you true super support. So you do super.xy and same thing in equals. So when would you use classes? Well, anytime you use class-like abstractions, of course, duh. But what are ES6 classes? They're prototype-based, just like you used to. The previous 2 slides have almost identical semantics. So if you don't want to use classes, go ahead, write all that prototype mess if you want. So they're mostly syntactic sugar. As a bonus, we give you working super. There are a lot of libraries today that tries to provide an API for super. They mostly work, but there's always edge cases that they miss. For example, if your superclass has an accessor, but in ES6, as a spec, we have to cover all the edge cases. We cannot leave a single edge case out. So we make sure that works everywhere. And also, we give you class-side inheritance. So if there was a static method on point, that would also be accessible through point3d. The last two explains why it's mostly syntactic sugar. For example, class-side inheritance cannot be done in ES5, because in ES5 you have no writable prototype. All browsers since IE11 allow you to do that, so you can do it if you want to skip the older browsers. Secondly, modules. Modules is a big work item for ECMAScript 6. Today there's two popular module systems, AMD and CommonJS. AMD stands for Asynchronous Module Definition, and as the name implies, it's asynchronous, which is good for browsers, because in browsers, you cannot do a synchronous load. If you do a synchronous load in your browser, the browser stalls. If you have animations, they will stop. The user cannot click anywhere. So that's bad. CommonJS is very popular in Node, but CommonJS does use a synchronous load to load your module definitions. But there's a tool called Browserify, which is a preprocessor or a build tool that takes all your Node.js modules and bundles them into a single JavaScript file. So then you can deploy that on the web. So this is what AMD modules look like today. You have a define function that takes a list of the modules you depend on. The define function is usually injected by your library, commonly something called require.js, but other libraries also define a define function. The second parameter to this define function is the function that will get called when all your dependencies have been loaded. And as you can see here, we have parser and parser, source file and source file. They have to map. They're one-to-one, the order matters. And in this case, where we only have 2 modules, it's not a big deal. But imagine if you have 10 or hundreds, it gets really messy. The final thing to point out here is a module. To export a value from a module, you use a return of that function. Similarly, the CommonJS version of this, the big difference here is that there's no wrapper function. The wrapper function is provided by CommonJS module loader. And that module loader injects the require function. And that require function does the synchronous load of your module and returns the exported value. And to return or to define what the module exports, you use module.exports equals, or you just add another property to an existing export. So in ES6, we give you a bit more concise syntax. Say what you mean again. There's no magic API here, it's just syntax. One thing to point out here is that the string /parser.js is not an expression. It's just a string literal. Nothing else is allowed there. You cannot have a function call in that position, only a string literal. Another thing to point out is that import and export only work at the top level of a module body. That means you cannot put them inside an if statement. There's no way to do conditional loading. They're purely static. And I'll tell you why that's important in a bit. So when would you use modules? Well, when your file gets too big, like 5,000 lines or whatever, it gets hard to maintain. But the main reason is actually for better logical grouping. If you split your code up in multiple files or modules, you have to think more about your API boundaries. You have to think more about your dependencies, and it makes the code much clearer. So what are ES6 modules? Like I said, we cannot ever do synchronous loading in the browser. But it looks kind of synchronous if you looked at the previous one. It looks very synchronous here, right? But these are static dependencies. Everything there is static. And that means that as we load the file, as soon as we see the import statement, we can start fetching the next file. We don't even have to do a full parse. We can do pre-parse. And as we stream in, we fetch all the files. And once they're fetched, we then do another pass over them to validate your imports and exports. So if you have a typo in one of your import names or export names, or if one of your dependencies suddenly changed their API slightly, you're going to get a static validation error before any code is run. And this is important. With other systems, you get errors at runtime after you've deployed your code. With ES6 modules, you're going to get a static error as you develop. And finally, ES6 modules give you cyclic dependencies. Both AMD and CommonJS have a hard time dealing with cyclic dependencies. And in ES6, it just works for free because the import and export variable binding are actually the same variable binding. So they just point to the same place in memory. The next thing I would like to cover is something that I'm sure everyone has run into. It's something new people to JavaScript hit all the time, and even experienced developers hit it all the time. So in this maybe contrived example, we have a menu button class that when you click a button element, it's supposed to show a menu. Pretty straightforward, right? So you add an onClick handler to the button, and then when that happens, you call this.showMenu, because you see there's a method called showMenu. Well, you're going to get a type error. Undefined is not a function. Not very useful, right? But most of you probably knows why this happens, and that is because inside that callback for the onClick handler, this is bound to the button. So in ES5, we added a band-aid to this with a bind function. So with the bind function, you can redefine what this inside the function will be when it gets called. In ES6, we provide a new syntax for this called arrow functions. Arrow functions are not just shorter and more concise than functions. They also have a lexical this. So when we look up this in the callback, we're going to look in the context of the outer function, outside the function, which in this case is going to be the instance of the menu button. And now this code works. So when would you use arrow functions? Anytime you see bind this, you should probably hit the delete key and change your function to an arrow function. Actually, I would recommend you to use it anytime you have callbacks. It's especially useful for when you use like array.map, array for each, array filter, because those tend to be very small functions. A little bit more about arrow functions in ES6. They're short and sweet. They have a single expression or a body. So the right-hand side of the arrow can either be a function body with curly braces, and in those cases you can have multiple statements in there. You can have multiple returns or no return, whichever way you want, just like a normal function. But you can also have a single expression, and that will have an implicit return. And like I mentioned, they have a lexical this, as well as the lexical arguments. But more importantly, they also have a lexical super, which comes in very handy once you start using super a lot in classes. Two more smaller features that I would like to mention. The first one is default parameters. I'm sure you all write code like this today, where you have an optional parameter called filename, and then if the filename is not provided, you use the OR operator, and then you compute something else. And in ES6, we just give you a dedicated syntax for this, using an assignment in the parameter list. So when would you use that? Anytime you have optional parameters. Even if you don't have a default value for your parameter, it's better to use these parameters, and you can just use undefined as a value. And why is that better? Well, it makes the intent clear. You can look at the parameter list and immediately see how many required parameters there are and what they are. And it also handles the issue where your OR operator incorrectly treats falsy values like the empty string of 0, which tend to be, if you think about your code carefully when you write it, it will work, but I'm sure there's plenty of bugs out there because of that. A similar feature is rest parameters. If you look at this very contrived example to compute the max of multiple parameters, you see here that we have a function that has a variable number of arguments. So anytime you use variable number of arguments, you have to get that out of the arguments. But argument is not a real array. It's a weird object. And most people like to work with real arrays, so they convert the arguments into a real array. And they use this very contrived API, array.prototype.slice.call arguments, and then the length they want to start cutting off at. And after they have a real array, then they can use reduce, map, filter, and all those nice features. So in ES6, we just get rid of a contrived call to slice. We give you a true array and say what you mean once again. So anytime you use arguments, I would say that you should probably refactor your code to use a res parameter. And once again, they make the intent very clear. You don't have to look through the code to see that it takes variable arguments. You don't have to read the documentation. And as I say, it's a real array. And ES6 is a really, really big spec. There are lots of other features in there. I was initially going to talk about promises, but over these 2 days, I've seen that everyone here knows everything there is to know about promises. So what? This is all pretty good, but when can I start using all these features? Now, correctly, yes. Browsers are working very hard to implement these things, and the latest browsers are shipping big parts of the spec already. And there's this website, I'm not sure you can see it on that one, yeah. There's this website which tracks the progress of the latest browsers. You can look it up online. As you can see here, Firefox 34 is actually doing pretty well, has lots of green. But there's plenty of red here, and the question is it too much red? Well, that's where Traceur comes to the rescue. So what is Traceur? Traceur is a compiler. It compiles ES6 and more to ES5, which means that you can write ES6 code, compile it to ES5, and it will work in all modern browsers. A little bit more about Traceur. It's a compiler written in ES6. So we have been dogfooding ES6 for about 3 years now, and we have upgraded the code as the spec has matured. Traceur was designed to be a platform for experimenting with new language features. So it does that really, really well. And a lot of the features that are in ECMAScript today were first prototyped inside Traceur. We also prototyped a bunch of other features that never made it into the spec, but that was the whole purpose of it, to show that, or we wanted it to work, but it turns out that those features didn't work, and we had to cut them. So Traceur is highly modular and extensible. This is because it was designed for this specific task. It was not designed to be a minifier. It was not designed to do random things that most parsers are. So a little bit more about how Traceur works. So like I mentioned, it's a compiler, and the first step we have to do is to compile. So we compile the source code into an abstract syntax tree. And after that, we transform that abstract syntax tree. So we take a tree, an AST, with a language extension, and then we transform that into another tree without that language extension. So it gets simpler over time. And in Traceur, we have one transformer per language extension. And then we pipe all those transformers together. So we start off with an AST that has all the ES6 features in it, and it gets simpler and simpler until we get finally to an AST that has only ES5 features in it. And finally, we write that out. So we use a visitor pattern to write the output source and source maps. A little about creating your own language extensions. So like I mentioned, it's not really important to do that for most people, but you can also think of these as a way to improve your DSL or do some code shaking or remove some code that you don't need, or like transform your code when you change your APIs. So I'm going to walk you through a very, very simple transformer. And the goal here is to remove debug asserts. As you know, writing asserts in your code can often lead to better programs. And especially when you start developing something from scratch and you don't have the time to fill out one of the edge cases, then you put an assert there and say, implement me. It's also good for adding preconditions that you assume are always going to be true. But once your product is stable enough, you hopefully not hitting any of those asserts anymore, you might not want to ship with them to a production server. So the goal of this one is to remove those assert calls. So we have this very straightforward standard assert function that takes a value, and if the value is falsy, we're just going to throw an error. So we want to transform this call expression, assert sum expression, to a no-op expression, void 0. We could also make a transformer that removes the whole thing, but that's a bit more complicated, and it takes longer to explain. So I settled for something simpler. And also, if you then use Uglify or a Closure compiler to remove dead code, it will most likely strip out the void 0 for you. So The first step to creating a transformer is to extend the parse tree transformer. The parse tree transformer is the base class for all the transformers in Traceur. And as you can see, we use the ES6 syntax for classes here. The next step is to override the write transform method. In Traceur, every single AST node is backed by a unique class. So if you have an if statement, there's an if statement node for it. And the if statement then contains a condition child, a then child, and an else child. And for the assert call, it's actually a call expression. And call expression consists of an operand child and an argument list child. So what we need to do here is just check if the operand type is an identifier expression. And if that identifier expression has a string value assert, we then go in to return a void 0 expression. If it's not an assert call, we call super and let super handle the recursive calls. And it's important to also call super here because you might actually have nested expressions like a function expression as one of your parameters. And you need to traverse into that one. Step 3 is to add the transformer. As I mentioned, Traceur has this pipeline of transformers. And we use one of these which we call from options transformer, which takes an options object. And depending on the values of those options, we append the transformer or not. And in this case, we only want to add the transformer if we are not in debug mode. So in debug mode, we want to keep it, so don't add it. That's it. And I have a patch. I doubt it's worth clicking on this. Nah, OK. Anyway, the patch is very, very small. Actually, the code I've shown you is the entire patch. And when you look at the patch in GitHub, 50% of that is just the copyright license header. Well, if I added a few tests, which I should have done, it would probably have grown 2 or 3-fold. So I would also like to talk a little bit about Angular language extension and AddScript. I know we covered it quite a lot already, but this is something you're going to have to learn at one point or another, so why not? So AddScript, it makes programming Angular better through language extensions. So previously we talked about ES6 and how that makes programming JavaScript better. But Angular AddScript is much, much more targeted towards the use cases that Angular tries to solve. And the 3 big ones, as I call them, is type annotations, type assertions, and annotations. The last one was called metadata before, and there's also something called introspection, which is kind of related to annotations. It's just different terminology. So today, we have type annotations. Well, we don't have type annotations, but a lot of people tend to write them anyway. And there are systems that actually enforce them, like Closure Compiler. And people today in JavaScript have to resolve to ugly things like JSDoc. And in this example, we have a repeat function that takes a string and a number and returns another string. So with AddScript, we move those type annotations into the code. And we use a colon syntax, which is what TypeScript uses. And they took it from ES4, which took it from Pascal. And Pascal probably took it from something else, even older. So it's a syntax that's been around for a long time. So what are the benefits of inline type annotations? Well, no more JS.comments. Hooray. So JS.comments lead you to repeat yourself, and we hate repeating ourselves. So, and also, with JS.comments, you have out-of-bounds data. You have to keep your parameter names in sync. You have to keep the order in sync. And when someone comes in and refactors your code, they have to update the JSDoc parameters and so on. And these things always get out of sync. And the only way today to keep them in sync is to have a preprocessor or a pre-submit pass that actually validates your code. And they're also very concise, so it's easy to read. You don't have to look out of the function. You just read the code, and it's right there. And another very important, maybe the most important part of type annotations is that it allows tools and IDEs to be really, really awesome. So some tools that you can imagine is a static type checker that validates your code even before you've run any code. So as you type your code in your editor, it might actually say, well, this function does not take a string, it takes a number. And you know immediately that you're doing something wrong. IDEs can also provide much better autocomplete because now it knows what the supposed return type is going to be. So the companion to type annotations is type assertions. So given the same function we had before, we now want to make these into runtime type asserts. And the way that Traceur today compiles this is to just sprinkle the code with a bunch of asserts. This is actually the code that's generated today, and I know we probably need to change it slightly. But as you see, the first step here is to just assert that the argument types are correct. S has to be a string, N has to be a number, and then finally we have to wrap all the return values with another assert. So we would assert that the return type is a string again. So type assertions, that keeps you honest. So even though you might have static type checkers, they will not catch everything, especially in a language like AdScript or TypeScript where you have optional types. You might have a single place in your code base where you have a non-type variable that suddenly you call a function that expects a string, but the non-type variable is actually a number, and then things go wrong when you don't expect it. So with these runtime type assertions, you will get an exception. So like I said, the catch is errors, both in the code and in the type annotations. Because if you don't actually enforce the type annotations, you might have errors in your assumptions about the type. And finally, type assertions can be turned on and off, whether you're in debug or release mode. So Traceur has this options mode or flags, which makes every single feature toggleable, so you can turn it on or off. And for production, you should probably turn this off. And the last feature that AdScript adds is annotations. Today, in JavaScript, you might want to attach some metadata, and it's really straightforward. Just add a property to your function. Really simple, right? Well, like Mishko said, what if your function is 100 lines of code? Then you have to add it at the bottom. Or what if you actually want to add some metadata to a class method? So then you have to go after your class body and then look up the method again. So you have to do the class.prototype.method name, .annotations, .metadata in this example, and then add that. So instead, we give you the @annotations, which just goes right with the function. And in Traceur, this compiles to basically exactly what we had in the first slide. The only difference is the name here. We set along annotations. But the important point here is that you can put your annotations right with your functions, not out-of-bounds data. So annotations don't really do much by themselves. All they do is they attach metadata to your functions. But, oh, sorry, this is out of order, but we can get to that later. But that metadata can then later be used. And in Angular 2.0, it will be heavily used for dependency injection and component to directive descriptions. But you can also imagine it being used for a lot of other things, like defining your data binding, or if your test framework might have annotations to say whether it's a large test or a small test, whether your test is flaky, and lots of other things. And like I mentioned, annotations are inbound, so they're not out of bounds. You can just read your code, and it's right next to the function that it applies to. So that was all I had to present today. And if you want to know more, there's an ES6 spec draft up on the internet. The final spec is supposed to be done in January. And once that is done, that spec goes to ECMA and ISO, and they will put their stamp of approval in June next year. So it's only 6 more months. There's a mailing list for ES Discuss. We talk about standard stuff. And then on Traceur, we have a GitHub page and a mailing list. And feel free to ask questions. File issues and pull requests are highly welcome. Patches are welcome. Thank you.